In this video, we'll look at the comparison theorem. Note that f is greater than or equal to g, which is greater than or equal to 0 for all x greater than a. Then if the integral from a to infinity of f is convergent, then also the integral from a to infinity of g is convergent. Let's think about that graphically. If we have a function, let's call it f, and we're trying to measure the area under that curve, and we find that it is finite. It does converge to a finite number. And we have another function, g, that is smaller than f. Will it also converge? So let's say this is g of x. If we know f is a convergent integral and g is smaller than f, then g, by the comparison theorem, must converge as well. Similarly, if we have f is divergent, let's say the area under this curve is infinite. This is a divergent integral. And then g is actually bigger than f. If g is bigger than f and f is divergent, then g must also be divergent. Another theorem that will be helpful when we are looking at the comparison theorem is this. The integral from 1 to infinity of 1 divided by x to the p dx is convergent when p is greater than 1 and divergent when p is less than or equal to 1. We'll see this come up in the next two examples. Let's use the comparison theorem to determine whether the integral is convergent or divergent. For the moment, we're going to focus on just the integrand. And let's focus on positive values of x. So for x bigger than 0, let's look at x divided by x cubed plus 1. And we want to compare this with something that we know a little bit about. In this case, we know this theorem. And when p is bigger than 1, it's convergent. Let's compare this with another fraction. Let's remove the 1 from the denominator and think about what just happened. When the denominator gets smaller, like it did in this case, notice the fraction is getting bigger. So we can say that the original integrand is less than x divided by x cubed. And then we can rewrite that as 1 over x squared if we reduce it. And that's helpful because we know something about this one. Using the theorem, we know that the integral from 1 to infinity of 1 divided by x squared dx is convergent. Again, recognize that this fraction is actually bigger, so if the bigger integral is convergent, then the smaller one will be as well. But take note of the limits of integration. We have the original is from 0 to infinity. X divided by x cubed plus 1 dx. We need to rewrite that as 0 to 1 x divided by x cubed plus 1 dx plus the integral from 1 to infinity of x divided by x cubed plus 1 dx. This first integral is just a constant. We have finite upper and lower limits, so we know this is going to converge to a finite number. This piece we just proved is convergent to using the comparison theorem. So overall, we can say that the original is convergent. Let's again use the comparison theorem to determine whether or not the integral is convergent or divergent. We'll focus on the integrand for now. And we want to compare it to an integrand that we're more familiar with. In this case, we can rewrite this as 1 divided by the square root of x. Notice if we remove sine squared and write it as just 1 divided by the square root of x, the numerator has gotten smaller. If the numerator is getting smaller, then this fraction is smaller as well. So we can say greater than or equal to, since this one is smaller. Now looking at this integrand, writing it back as an integral, we have 1 divided by, think of that as x to the 1/2 dx. This integral we know is divergent. And if a smaller integral is divergent, then the bigger one must, by the comparison theorem, be divergent as well.